So thread pitch. Let's have a little fun and talk about thread pitch, and I'll try to keep it kind of sweet. So a thread pitch, TPIs, that is, and these springs are going to help you understand how it works. It's per inch. As you look on the Bolt Depot's gauge guide, you would line even this lag screw up with this scale, and you could count the TPI in it, threads per inch. This is the Bolt Depot's 1/4 inch by 3 inch lag bolt hex flange head. So they just look like threads around there, and to help you visualize what those threads are doing per inch, I actually have, let me put down that spring, I'll come back to that, a spring to help you visualize what's going on. You can see the spring is matching that thread pitch pretty awesomely, right? And now I've got a little spot, a hump to get over right there. But it's not stretching the spring out or anything. It's matching that thread pitch. With that said, let's go ahead and back this out, and let's look at what the threads look like. This is your threads per inch. Let's put down the bolt in the background here. So you can see that, and grabbing this, this is what this bolt in the background looks like. It's this ramp. See the ramp? You start here, screwing into the wood, and it ramps, and it comes around again, and around again, and around again. As it's going down, spiraling into the wood, it's wedging its way into the wood, screwing its way into. All of the bolts and screws are the same. Now, let's go ahead and do two things here. I'm going to show you, sort of helping you understand clamp force. So right here would be a material that you would put between here. Let's grab this same helix, this same spring. Let's thread it back on there. And you're going to, the spring that's in the background, you see it's loose. That's the material you're going to fasten up to. And you go to screw in there, la 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 la. It's still loose. Then you start screw. You finally get to the back of the material. This is where you get your false friction now. Obviously, we're not really, this is still loose. It's not really tight. But this is where we get torque false readings from sometimes, and also at the surface down here. The surface could be a nut, it could be the wood, it could be anything you're screwing or securing your bolt into, or your screw. Now, I'm going to still crank this in, and as I do that, this will now compress. And we see it compressing. This is our clamp force now. Now this is really snug. That's our torque that you're trying to do to get this so it's so taut that it's tight, that it won't move, that you resolve your issue that you're trying to resolve, whether it be vibration, clamping something in there so air doesn't get out, so fluids don't get out, whatever it may be. This is why it's so important that this clamp force is maintained. And different things that feed that are back here, mostly the bolt rubbing against what you're trying to clamp secure, and the threads themselves. But these are your two friction points. Between is normally a gap. There's usually a space. So you can see if there's a space in there, that's not the problem. See how I can move the spring? So the torquing issues are the back of the bolts, and where the top of the threads, rather, internal threads of your, whatever you're tamping into, a motor, mount, or bolt, or wood. And if you keep going, if this was wood, you can strip out the wood. We obviously understand that. Let me show you, using the Bolt Depot's metric gauge, what that would look like in a side profile. This is the screw. Remember, all I did was show you the spring, and now this spring becomes the screw. Look on the back side of this as we watch it. As I turn, you see how it's ramping? It's coming around in a ramp. Whoops, too hard on that. It's coming around in a ramp. The next, as a spiral, it's just slowly wedging its way in behind it, just shimming, if you will. See, we have two surfaces that are rolling in. This is rolling in here, and there's a ramp. The next one is rolling in too. You can see these aren't affected yet. But now, if you can't go any further because you now have something between there, and you still keep putting this taut, you still keep rotating it, you still keep, well, that was brilliant. I lost it, but guess what? I have a backup. So we'll still go with that. And you're screwing it in, and this is the larger scale of it. And now you can't go any further because this surface between Let me help you out. Right here is no longer will compress anymore. It's a piece of steel. You still keep turning. What happens is you're now elongating your bolt. This is the bolt. But the bolt can't move that much like a spring. It can only move a little bit, you know, thousandths of an inch. And you're still adding that torque. It's still doing the wedging, trying to lock in. But you're also making a rotation. That wedge now works against you in the bolt because the forces are equal coming back. And it will split your bolt and consequently get a broken bolt, broken screw, whatever it may be, because you've reached the maximum torque that tension would allow. The tension is the elongation happen, the spring on this side. On this side we don't have a breaking off, right? There's nothing there. There's nothing, it's free. It may be in a nut, but only the first 4 threads or so experience the forces. You're a much different format because on this side is where the stresses are happening. This is the part that can no longer compress, the material between it. So now this is the part that's stretching. On this side, this is okay. It can rotate inside there, and it has that wedge acting going on. This is the bolt side, and it doesn't have a problem with it. This is the one that stretches and breaks. Kind of simple, isn't it? Let's look at this real quickly. This is a 1/4 bolt. 1/4. What I did was I wrapped a spring around it. And the spring doesn't match up to the threads, but it's just a spring. If I were to pull that out, I could match the thread count. And all I would have to do is match 20 of these rotations per inch. And there's your thread count. Does it matter that it's bigger, wider? No, it just needs to be 20 per inch. Looking at, just push that away. Looking at these guys, they're kind of cool. These are the springs again. So let's look at what a thread count looks like. I have my little cheat sheet over there. That says it's 9. So these screws now, we're calling them, this helix, these are screws, all are the same. One seems bigger than the other, wider, but they still have a count of 9. 9 threads per inch. Using the BOLTDEPOT gauge, if I put it on here and I count these threads, of course you can pause it, you'll count 9. 3, 6, 7, 8, 9. It's just you know, I've got an issue with this little thread thing I have here, the way it's threaded, but it's 9. And for our purposes, it's going to be 9. So I go to my 9 count, and I put it on there. 9. So this is what a 9 threads per inch bolt looks like. The helix looks like that. Round and round. And so it does the shimming the same way. As it rotates, the ramping, it screws in there, it elongates and puts clamping force down. This is the same as this one. This is also a 9, except for now it has less surface area because it's a smaller diameter. But it's a 9 also. So we grab the 9, and you see, it's a 9. So that's when it matters. If you want more surface areas, it gives you more clamping force or surface area to bond with. That's a 9. Also, this is a 9. Mind you, don't pay attention at the beginning because it's got a bit of an issue. But this will help you visualize what your bolt is doing, what your screw is doing. It's a helix, and it's acting like a ramp, ramping its way into your surface, creating a clamping force, which we always are doing with all bolts, a holding force into this section where my hand would be. This is where it breaks also because at some point it can no longer clamp anymore. So I'm rounding it up for you guys. It still keeps trying to clamp this ramp. It's a beautiful design. This helix will still keep trying to shim its way in. As you shim its way in, you're basically shimming apart this spring, which is the bolt, and you're breaking your bolt as you have the rotational torque or rotational forces also happening. Kind of cool. Grab a spring, and you can duplicate any thread counts you like. So this is roughly what it looks like with thread engagement. That's the spring, and that's the bolt in the middle. As you'll see, I'll let go of the spring in a moment. I'll rotate it just a little bit. And there's the spring. As I come back out, you can see it. And there's your spring lining up with the with the thread count. This is the quarter 20. Sorry, we got George in the background, my cat. He's hitting my elbow pretty hard here. But there's the quarter 20, and that's the spring. As you can see, even the spring has, even though it's taut, it still has a count that it has to respect and honor. Well, so now, give me a second. I'm holding this, but I need you to visualize why the nut doesn't fail. A reason why the nut doesn't fail. This is the, I use a spring to show this will be a nut. So pretend like we're looking into the internal of, say, 4 threads. 1, 2, 3, 4, or 5 threads. This is the bolt. And this is the bolt, the remaining part right here. It's going to screw into the nut or the surface, the surrounding surface, the, say, the engine part. This already has engagement of, let's call it 4 or 5 threads. See how nice and snug that is? Well, as we come down to the end, this bolt here is still trying to engage into the nut, this section here. These are experiencing the most force. This first one, the second one, and then these last 2 drop off the forces. But the first 2 are experiencing the most amount of force. This is an incline, remember the ramp, if you will? It's ramping its way into this bolt that already has a balanced 4 threads of the bolt attached to it. So its forces are, here's 100% of the forces, let's call it. There's nothing on this side at this point, right? There's tension on this side. And with that tension on there, as you still rotate in this incline, that ramp, it can't go it can only go so much. And right at the root, right there, is where it experiences its failure. It's still trying to rotate in. This is the one that mostly breaks. I find this one outside here, not the one behind here. It is possible, but this guy seems to be the one that wants to break the most of all my bolt experiments. It's possible that it can snatch it off right below there, depending on the incline. Now, as you rotate it, again, the forces can no longer resist the tension inside the bolt, and the clamping forces created by that bolt, and that nut having full engagement. It's stronger than this little bit of section out here that's still trying to engage. This section here is trying to work its way into the nut. Or an engine block, as you're trying to screw into the engine block. Say you have 40,000 pounds of force or 80 pounds of torque on this. It's also pushing back at 80 pounds of torque. So the screw or your bolt, you're still trying to turn in against those forces of the threads engagement also. So if this is the nut, it's fully engaged the screw at this point, or the bolt. And at this point, when you're still trying to create more clamping force, you have that ramp. That's ramp I showed you in the beginning part. It's trying to dial its way into these forces here. And it's meeting resistant forces also. This already has some resistant forces on it. This is meeting the screw or bolt is now meeting those forces, and you're trying to overcome them and still screw down and get more clamping force. Also, you have the product you're trying to clamp may not compress anymore. And once it can't compress anymore, you're left with just putting tension on the bolt. If you're putting tension on the bolt, if you go too far, if you still keep trying to rotate it, either the head will break off, which you have a cheap bolt at that point, or it will break right about here at this root. I find this root is the weakest point mostly, sometimes just right between this first one also, the first connection. But this being the weakest point, usually breaks there. And then you're left trying to pull out the remainder of the screw, right? So thank you for taking the time to watch, and please subscribe. And as everyone else says, don't forget to hit the bell, if the bell still exists on YouTube.